Okay, welcome back. Now I'm going to do a demonstration. I'm calling it Charles's Law and absolute zero temperature. So it's going to be similar to the video that I did, the demonstration on Boyle's Law, where I graphed pressure versus 1 over the volume, and I showed that it's a straight line. In Charles's Law, we're going to work on the relationship between volume and temperature of a gas. So we have PV equals nRT, where the pressure of a gas is constant, right? Then volume is linearly proportional to temperature. So that is what I'm going to be proving here. Volume is proportional to temperature. So I'm going to be getting 3 data points from this for volume as a function of temperature. One of the things that I want to show is that this gives you a straight line. It should be giving you a straight line here. The other way that I can use this demonstration is I can actually predict what the temperature of absolute zero is. This is, I'm going to be plotting it as a function of Celsius. So this is 0 Celsius. So then I can extrapolate back and I can find out what temperature we must reach so that the volume of the gas reaches 0. So when we reach absolute 0 Kelvin, right? The gas should contract, and it should eventually have no volume at all. So that point where it has no volume is the absolute zero temperature. So we can extrapolate the graph backwards and we can see what the temperature of the absolute zero is. I've done a couple other demonstration videos that you guys can watch. One is the Boyle's Law. In Boyle's Law, we were concentrating PV is a constant, right? So we said P was 1 over volume. So I graphed pressure versus 1 over the volume, but I was doing only the height because the area, surface area of the tube wasn't changing. So I graphed 1 over the height. Then I showed that this gives you a straight line. I got several data points and I showed what kind of straight line gives you, how close to a straight line that gives you. The other video that I've done is also similar to this, where I took a pressure gauge and I put it into different containers of water, and I found the pressure. So there I was concentrating on the relationship between pressure and temperature. So one is pressure and volume, the other one is volume and temperature, and then the third one is pressure and temperature, right? PV equals nRT, the relationship with pressure with temperature. So in that demonstration, I graphed P versus T, and I got 3 data points. Then I proved that those points give me a straight line, and then I extrapolated it backward and I got the temperature for absolute zero. So it ended up being a very good result to what it's expected to be. So let's see how this lab goes. So the way that this is going to work is I have a test tube here. It's 50 milliliters is the volume of the test tube. So I put a stopper on it and it's getting warmed up in water. So what's going to happen to the air inside of that test tube? It's going to start expanding because the water is heating up the test tube and the test tube air. The air expands and it leaves the test tube, right, through the opening here. The opening is open, so the air expands. After the water starts to boil or reaches near boiling, I can take out the test tube and I can put it into different water baths, right? One, I have a water bath here in the middle. I can find out what the temperature of that is, right? So the temperature of this one, the middle one, 28.0 Celsius. 28.0 Celsius. So what's going to happen? When I take the tube and I'm going to put my thumb over it, over the top, right? I'm going to put my thumb, I'm going to close it, then I'm going to take it and insert it into the water, then I'm going to release my thumb, right? When I release my thumb, what happens? The air inside of the test tube decreases in volume, right? Why? Because it gets cold. When I release my thumb, because the air contracts, the amount by which it contracts, water gets into the test tube, and a small amount of water gets in there due to the contraction of the air. So then I lift that up and I measure how much water got in there. That tells me how much is the final volume of the air. I subtract 50 milliliters, which is the original volume of the air in the test tube. That's the original volume. Then I subtract from there the amount of water that got in there, right? And then I find out the final volume. Then I put the test tube back into the container of boiling water, right? I let it heat up again. Then I do the same thing. take it, put my thumb over it, put it in a bath of ice water. So the temperature of the ice water, okay, the temperature of the ice water is 2.0 Celsius, 2 Celsius. Okay, now the water is at the boiling temperature. I'm gonna measure its temperature right here. Okay, 97.5. At this point, I'm gonna take the test tube out. 97.5 was the temperature of the water. You want to close the thumb right here. Put the test tube completely, immerse it in the water, right? Then let go of your thumb. A little bit of water will get inside of the test tube. Okay. So you can see here, the test tube has a little bit of water in there. Okay, because the air inside of the test tube shrunk, contracted, right? And so that space was filled up with water. So let's determine how much water that is. 5, 5.5, 6, 6.5, 7, 7.5. Okay, that's about right there between 7 and 8, 7.5 millimeters. Okay, so then the original volume of the air in the 97.5, the volume of the air is 50 milliliters, right? When I put it into the temperature, the regular room temperature water, right? How much 7.5 milliliters of water came in there, right? So that means the volume of the air, the final volume of the air is 50 minus 7.5. So 50 minus 7.5, and you get 42.5 milliliters of water. Let's retest the temperature of that water. I get 26.3 Celsius. 26.3 Celsius. Okay, so we can change that over here. 26.3 Celsius. Okay, now let's put the test tube back in. Close the stopper. Okay, so now more water got in there, right? Because the air contracted more. So you can see here the level of the water is more, right? See, that's how much it is right there. Now I'm going to measure how many milliliters that is. 15, 15.5, 16, 16.5, 17, about 17 milliliters. So then what would the volume of the air be? 50 minus 17 would be 33 milliliters, right? That would be the volume of the air. Okay, now we can do a plot of volume versus temperature. On the left side, we can put the temperature. On the right side, we can put the volume. The lowest temperature will be 3.6 Celsius, right? The volume of the air will be 33 milliliters, right? The next temperature will be 26.3 Celsius, and the volume of the air will be 42.5, right? Because 50 minus 7.5. And then the original temperature of the water is 97.5, and then the volume of the air is 50 milliliters, right? So let's do that plot on Excel, and let's see what kind of graph we get. Okay, so I open up Excel. On the left column, I'm going to put temperature, and the right column, I'm going to put pressure. And the temperature, my data point was 3.6 Celsius. Then the next temperature was 26.3. And the next temperature was 97.5. And then the next column was volume. So one of the things we want to see is this a straight line? How good of a straight line is it? And then what's the slope of that line? And then let's calculate the temperature of absolute zero from that, right? Just by doing a simple experiment like that. Okay, so let's go to insert, scatter plot. Okay, so it is not that consistent. It's not that good of a straight line. You can see that it kind of plateaus. So again, I would have to repeat this if I was doing it. I do have one data point here that seems to be either up. Maybe this needs to be up more, or maybe this needs to be a little bit lower. Okay, so you can see it's not a perfect straight line. So let's get the error from that. The layout trend line. So I'm going to ask for the display equation on the chart, display the R squared value. Okay, so the equation is going to be, let's make the font bigger here. Here, this is the volume. So one of the things we wanted to show, volume is linearly proportional to temperature, right? R squared value 0.8775. So it's about 12.5% error, 12.25% error, right? So if this one was 1, that would mean perfect straight line. That would mean it is a perfect straight line and the fit is excellent, right? So we're not getting that good of a result. So you can say 0.8775, about 12.25%. And then this is the equation that we're getting, so for the volume. So let's put that down and then do our calculation from that. Okay. Now if I put the same data into Logger Pro, let's see what Logger Pro gives me. It might give me slightly better result or worse result. It's definitely going to be a little bit different. So I put the data over here, right? So again, it gives me this kind of connection, right? Then I go over here and I say, okay, give me the linear fit. So the slope 0.1629, the correlation 0.9367. So actually, it gives me a better correlation value, 0.9367. So it's correlated. How good of a straight line is that correlated to? 0.9367. So we get only about 7% off there. So let's write that one down. V equals 0.1629 T. The slope that it's giving me is the same. Exact same slope, 0.1629. The y-intercept, 34.92. Pretty much the same as the Excel, right? So plus 34.92, the correlation value 0.9367. Okay. So you can see here, these are the results that I got from Excel. I can use the better correlation and I can say how much off am I from being a straight line. So then my percent error is going to be 100% times 1 minus 0.9367 over 1. So that's going to be about 6-7% off from being a straight line. Okay, so now let's do the temperature of absolute 0. So set the volume equal to 0. Since these two equations are pretty much the same, I'll use this one since it has a little bit more sig fig, like 916. So then I'll put the volume equal to 0. Then I say 0.1629 T plus 34.916. So calculate what temperature would cause the volume of that air to go down to 0. And then that's going to be the temperature of absolute 0. So then you're going to have Celsius. That one I'm not really close to because we know that the temperature of absolute 0 is going to be negative 273.15, right? So if I was doing an experiment, I would repeat this and I would see, okay, which one of my readings is off? Repeat this. Or the best way to do it is do this at multiple temperatures. Find the temperature of the air at multiple different temperatures. Like if I have a ice water bath, let's say I have a regular temperature water, then I have temperature of water at 45, another one at 60, another one at 80, another one at 95. If you put them in those ones, even if one of them is off, that's likely to influence your result less, right? So then overall, you're going to get a better straight line, more reliable straight line, and then you do this multiple times. So this one just kind of illustrates to you the idea. So now let's take our result compared to this, just take their absolute value, right? So percent error is going to be 21.5% error. 21.5% error. So it's kind of on the high side, but Since I only had 3 data points and I didn't repeat it to make sure my results were accurate, I'm still satisfied with that result. So you can see the basic idea of this is we proved that the volume is proportional to temperature, and we also showed how to calculate the temperature of absolute zero, an experimental method. Okay, thank you very much.